Everybody, welcome to my Physics 2211 Lab Report 5, the Falling Slinky. Here's a table of contents. First, we're going to be going over purpose and introduction. Second, we'll be talking about physics principles and a preview of findings. Third, we'll be going over experimental details and tracker. Fourth, we'll be going over code details. Fifth, we'll be going over results and possible errors. And finally, we'll be talking about some questions raised. So, introduction and purpose. The purpose of this lab is to fulfill the following. Analyze a falling slinky and the forces acting upon it, create a glow script model to reflect the slinky's predicted motion, and compare the real world and theoretical models. These, when completed, will demonstrate the following physics principles: Newton's second law, drag force and weight force, and tension. Newton's second law dictates the activity of objects in motion, and it states that F net equals the change in momentum over the change in time. This is always important to consider when something is in motion. Next, we're going to be talking about weight force, or the force of gravity in this case. So the force of gravity near the surface of the Earth is equal to negative mg, where m is the mass of the object and g is 9.8 meters per second squared. Now, drag force is the force acting opposite to the motion of an object, proportional to the speed squared of the object. So as you can see in the formula on the right, drag force is equal to negative b, b being the proportionality constant, velocity squared. And then in our case, since drag is operating in the y direction, then it will be multiplied by j hat. And then tension is the force experienced by a string or cable when it is pulled from the opposite end. So in this case, the upper part of the slinky will be causing tension on the lower part of the slinky with T equals mg, which directly offsets weight force, causing static equilibrium until the top of the slinky hits the bottom of the slinky, after which we see drag force begin to work on the system. So in this case, the system is the slinky, surroundings are the air and the air operating via drag, and the earth operating via gravity. And a brief preview of findings are that although the computational model appears to have overcompensated a bit, the experimental findings in tracker and the computational model are largely similar and reflect that tension, drag, and gravity are the primary forces acting on the system. So initial conditions are that initial velocity is 0 meters per second, initial position is negative 1.4 meters, and that's for the bottom of the slinky, and the motion is in the y direction. You can also see my tracker video on the right there, and these are the graphs generated by that tracker video. So x motion, I multiplied it by times 10 to the negative 2 to scale it a little bit. So as you can see, the x movement is very negligible. It's in the hundredths place of decimals, so I considered it to be negligible for calculations. And then y motion begins at negative 1.4 meters, roughly, and then at about slightly before t equals 1, then that's when the top of the slinky hits the bottom of the slinky, and then tension is no longer operating, and then drag takes over, and drag and weight force result in the slinky falling to the ground, which is then seen at a little bit more than t equals 1 when you see static at about negative 1.7 meters. So put this in my computational model. I had some initial conditions. I looked at the average mass of a slinky, found 0.218 kilograms, and went with it. Ball position and ball velocity were given from the experimental initial conditions. And then the delta t was based on frame rate. G equals 9.8 is the constant in the weight force formula. J hat, since we're only dealing with movement in the y direction, we have the vector being 0, 1, 0. And then our proportionality constant is 28.55. Now, for our actual computational model, we have the weight force being equal to negative mg and the force of tension being equal to mg. So as you can see, F net equals W plus Ft will cancel since those are equal and opposite, and that results in the static equilibrium that we see in the video and in the computational model. And then on the right side, after the top of the slinky hits the bottom of the slinky, then you have weight operating still negative mg, and now you have drag, which is negative b, which is our proportionality constant, multiplied by velocity squared, magnitude of velocity squared. And then that's going to also operate in the y direction, right? And then F net is going to be weight plus the force of drag. And the reason why drag doesn't operate on the left side is because the bottom of the slinky is not in motion. And the reason why tension doesn't operate on the right side is that the top of the slinky has combined with has collided with the bottom of the slinky, and thus there's no longer a tension operating on the bottom of the slinky. So this is the computational versus experimental position graph. So as you can see, there were some tracking errors by me before t equals 0.25, where I didn't get the starting y position exactly right, and that led to a difference in starting position for the computational experimental models. And that's why once the slinky hits the ground after t equals 1, then the computational model is a little lower than the experimental model. It's because the starting conditions were different. However, you can see by movement, then the experimental and computational models largely mirror each other, with tension and weight causing static equilibrium until slightly before t equals 1, and then the top of the slinky hits the bottom of the slinky, and then you have drag and weight force, where weight force overrides drag, causing downward motion until the slinky hits the ground. So the possible sources of error here are tracking errors, which I talked about, and then the man who released the object may have inadvertently applied a downward force, which is actually one of the what-if questions I discussed. A collision could have occurred when the top of the slinky hit the bottom, so that would mean we would need to consider the movement in not just 2 stages, but we would need to add a third. However, I don't think the collision resulted in a lot of force being applied to the bottom of the slinky, and if it did, I think it was negligible. And then the starting position was not consistent, which is responsible for some of the variation on the left side that you can see there. So some questions raised are: what if the top of the slinky was thrown down, right? So force applied downward in this case would make the slinky closing time faster, since negative y motion would be negative mg plus force applied, but the bottom of the slinky would still not experience any motion because the tension force would increase in magnitude proportionally to downward force, right? And then for what does it mean when the bottom of this slinky transitions from being in static equilibrium to moving? What does that mean for the forces acting upon it? So we've harped on this a little bit, but before t equals 1, the bottom of the slinky's free body diagram would have weight and tension canceling out, resulting in static equilibrium, while after t equals 1, or a little bit before t equals 1, then the top of the slinky has fully collapsed into the bottom. So there's no longer tension, only drag, and drag doesn't overcome weight force, so the bottom of the slinky falls to the ground. And that was reflected in this model here. Hope you learned a little bit about physics and enjoyed my lab report. Thank you.